Hello, greetings from Rutgers. We would like to present to you Giga graph cities. Our aim is to provide a means of visually exploring large graphs. But what does it mean for a graph to be large? For computers, we consider a graph to be large when it doesn't fit in random access memory. But for us humans, we are further limited by how much we can perceive. This is partially due to the physical constraints of our screens, but also the computational ability to allow a user to manipulate layouts in real time. Thus, a desirable graph exploration system should be computationally efficient for large graphs while providing interactive control without overwhelming the user. Our general approach is to decompose graphs into fixed points, and then decompose the fixed points further into waves and fragments. We map these subgraphs and similar clusters of subgraphs into various city metaphors, and design the system to navigate the city metaphor visually. Previous work proposes a decomposition algorithm that partitions a graph into sets of edges called fixed points of degree peeling. These fixed points are visually represented as layers in order to break a large graph into meaningful and manageable chunks. As the name suggests, however, the same decomposition cannot be used to further decompose fixed points. So, to deal with large fixed points, we propose a new decomposition into graph waves and fragments. Similarly to how fixed points form an edge partition of a graph, waves form an edge partition of a fixed point. Waves are constructed from a sequence of fragments in the following way. Given a fixed point with minimum degree k, we take the vertices of degree k as an initial seed set. In the example on the left, we have a fixed point of minimum degree 2 and an initial seed set S00. The edges with at least one vertex in the seed set are labeled as the first fragment and removed. Here that would be the blue edges. Once removed, the degree of the fragment vertices that were not in the seed set are updated, and those with degree less than k are selected as the next seed set, S01 in this example. Again, we label the edges going out of the seed set as the next fragment, remove them, and update the degrees of the affected vertices. We repeat the process until there are no remaining vertices, or the remaining vertices have degree equal to k. All the edges removed so far are labeled as the first wave. We start again with a seed set of degree equal to k and repeat the process until the fixed point is empty. Here, the blue and green edge fragments make up the first wave of a fixed point of minimum degree 2, and the red and orange fragment make up the second wave. We construct building metaphors for the wave decomposition consisting of circular disks connected by frustums. The size of each disk indicates the number of seed set vertices of its corresponding wave, and the volume of the frustum indicates the number of edges in the wave. A graph city contains multiple visual components. First, each fixed point is mapped into the building representation as was just discussed. Here are two sample visualizations of fixed point buildings with about 10 million edges each from the Friendster social network. Then, the fixed point buildings are bucketed according to similar size, and the buckets are visually arranged in a spiral layout. Here is an example of the spiral layout for fixed points of the Friendster social network. Large fixed point buildings are displayed individually, whereas buckets of many small buildings are given an additional visual mapping into grass patches. If you look in the full city view of the Friendster social network, you can see that the small fixed point buildings have grass patches, indicating many similar fixed points of similar size, whereas there is no such indication for the large fixed point buildings. In order to show how different fixed points are connected, a road network is drawn centered from a selected fixed point building, indicating shared vertices with other fixed points. Here is an example of the road network from the graph city of the patent citation network. Observe the following computational times of fixed points and waves and fragments for 3 datasets. Note that for the Friendster network, which has 1.8 billion edges, the computational time totals to about 8 minutes and the rendering time to only about 10 seconds. We represent fixed points as collections of waves through the metaphor of a building with floors. Each wave maps to a floor with its volume and disk areas corresponding to its size and edges and vertices respectively. The color hue indicates density. A building floor corresponds to the subgraph induced by a subset of vertices. Each floor is represented by 2 concentric disks, one above the other. The radius of the bottom disk encodes the number of vertices in the seed set of the starting fragment of the corresponding floor. The radius of the top disk encodes the total number of vertices besides the seed set vertices. The top disk is placed at the same height as the bottom disk of the next floor. A frustum between the bottom and top disk of a floor is set to have volume encoding the total number of edges of the corresponding wave. Since the radii to two disks is already determined, the height of the frustum is calculated from the desired volume. A special fixed color map across the entire graph is used to encode the density of a variety of induced subgraphs. For example, the color of a frustum represents the density of the set of edges running between the corresponding two floors, and the same color map is used to highlight the density of the connected components within a floor. Connected fixed points are grouped together into buckets according to the number of edges. We render a building for the largest fixed point in each bucket. A few fixed points in the bucket are uniformly sampled to be drawn as bushes on patches of grass. The dimensions of the grass patch indicate the total size and number of other fixed points. Bushes are a rougher representation of fixed points than buildings. To generate a bush, first a skeleton is created based on the same parameters of a given fixed point as those used for the building representation. Then, a few iterations of an L system are executed with initial points distributed along the skeleton in order to render the final bush image. The skeleton consists of a central stem with branch segments coming out at points in between. These junction points are spaced the same as the disks in the building representation of the fixed point. Thus, the length of stem segments corresponds to the height of the respective frustums. The inclination of the stem segments ranges from 0 to 45 degrees off the vertical axis, based on the density of edges in the frustum, 0 degrees corresponding to 0 density and 45 degrees corresponding to density of 1. Two sets of branches are produced at each stem junction corresponding to the inner and outer disks in the building. The number and length of branches encodes the number of vertices represented at that level. The inclination of the branches is proportional to the density of internal edges for that level. All branches are equally spaced at the junction, and phase angles at successive junctions are randomized. The flags on top of buildings display various summary information. For buildings that are alone in their bucket, the flag shows the number of floors, the peel value, and the size of the corresponding fixed point. For buildings part of a larger bucket, the flags show the number of duplicate fixed points, and a vicinity diagram, which is a mini-city representation in itself. This will be explained later. The height of the flag encodes the total number of edges in its fixed point, and its width encodes the total number of vertices. The length of the flag pole is the overall edge density. The graph city is the total collection of building, buckets, and bushes. The city is drawn in a spiral layout with larger fixed points in the center. Additionally, we draw a street network between buildings to indicate the amount of shared vertices between the corresponding fixed points. Here we show an up-close view of the graph city of the Friendster social network, which has over 65 million vertices and 1.8 billion edges. Notice that the outside of the spiral has many buckets of small fixed points, whereas the inside of the spiral has a handful of large fixed points which stand on their own. This is indicative of the fact that the dataset follows a power law, which makes intuitive sense for a social network. This view is a close-up of the graph city of the movie keywords co-occurrence network, which has only over 200,000 vertices and 115 million edges. Notice how it has much shorter buildings overall, indicating both smaller fixed points and fewer waves and fragments per fixed point. And this view is of the graph city of the patent citation network, which has over 3 million vertices and 16.5 million edges. The tallest building in this city seems to stand out a bit more in having particularly large floors. This means it is a big fixed point with relatively few waves, where each wave is itself relatively large. Each city can also be viewed in night mode, which adds a checkerboard pattern of lights to all the building floors. The light intensity at each floor is proportional to the number of vertices shared between the set of edges represented by that floor and the complement with respect to the whole graph. Selecting a building allows a user to explore the local fragment structure of the graph for that fixed point. The fixed point is drawn in 3D as a metagraph of connected seed sets. Then, selecting one of the metanode seed sets will bring up a view of the corresponding subgraph. In addition to the city, we produce a summary sculpture for an entire dataset. This sculpture gives a preview of the distribution of fixed point peel values and sizes. The aspect ratio of the sculpture encodes the average gap between consecutive peel values. The taller the sculpture, the larger the average gap. Although large fragments are rare, we still want to offer the user a way of exploring their structure. To draw large fragments, we propose a two-step iterative process. First, we delete all edges with peel 1 vertices as endpoints. Then we perform a maximal matching edge contraction. We repeat these two steps until the remaining graph is small enough to be drawn. To summarize, we take as input a large graph. We use the iterative edge core decomposition to decompose the graph into fixed points, and then further decompose the large fixed points using the wave decomposition. We group together similarly sized fixed points and map the output of these decompositions into a city metaphor with buildings and bushes. The city is rendered as part of an interactive interface, which allows the user to select buildings and explore their local substructure. Each bucket is also processed into a similar city metaphor that we call its local vicinity. Starting from the main city view, a user can zoom in to a singular fixed point building to see waves as floors, and then zoom in further to see their fragments. Zooming into the fixed point buckets, however, reveals its vicinity, which contains a mini-city of similar fixed points. When exploring the city, users can annotate subgraph patterns indicating their findings, and add the corresponding subgraph patterns to a pattern gallery. Here are some interesting metadag structures that we found. One tail-like structure from the Friendster social network, a DNA or ladder-shaped portion from the movie keywords network, and a small lamp-like structure from the patent citation network. Our current work includes exploring the semantics of waves to gather insights into the practical application of the wave decomposition. The picture on the right is a fragment from a patent citation network. We show the category and publication dates for a few patents, all related to chemical and medical processes. Currently, we are working on extending our approach to allow for streaming and more functional end-user features. Also, we are interested in exploring how to use subgraph patterns found with our interface for semantic data summarization. We are also interested in investigating which graph problems can be more easily solved by composing solutions of the fixed points, waves, and fragments. Thank you for watching this presentation, and special thanks to the NSF for supporting this project.